Good morning, everyone. So on the agenda for today is that I want to talk through all of your questions. So I'll talk through the questions that you've submitted, but I'll also leave plenty of opportunity for you to ask questions. I know this whole proofwriting business and the division algorithm and all of these things are all very new, so I want to make sure I give you plenty of time to talk about all of the various pieces of that, to ask anything you want. Then I'll give you time for the quiz so that you can turn that in later today. And then Friday, don't forget we have a test that covers everything we've done so far. So this is from the beginning through proof by contrapositive. So in particular, the week 3 videos are not on the test, I should say. Okay, but expect that the test will have lots of proof questions, but also some questions where it just asks you to negate something or write the contrapositive or etc. out of that variety of things. I'm not planning to do questions. I want to give you the full time to work through the test on Friday. So I will just post the test so that it appears at 11 on Friday and let you have until 1 to turn it in. Before I jump into the math-specific questions, I should also remind you, I do have office hours tomorrow at 11. And so if you have more questions that arise between now and then as you're preparing for the test, that is definitely a good place to drop by and ask them. You're also welcome to email me. A lot of times when you're working on a proof or something like that, you'll have a question that really can be answered in a sentence, and I could just reply to it. So if you do send me emails, I will reply, and if I think it's something that's more in-depth that we need to talk about, I can reply and tell you that as well. Okay. My goal is, of course, to grade the quizzes today and have the grades and comments posted by tonight so that you have the feedback going into the test so that you sort of get a sense of where you are in terms of writing proofs and what you need to work on, just so that you're not sort of doing it first on a high-stakes test. Okay. Before I talk about math, and I promise I'll talk about the math stuff that all of you have submitted and asked, are there any bureaucratic questions just about the test and quiz and et cetera, et cetera? I should stress for the test, you're more than welcome to use your notes or or whatnot. So don't worry about memorizing everything before then. Okay, so first question I'd like to go over out of the questions was someone asked about the definition of multiple, and I'll go over that and some of the related definitions and how that fits into our picture. So here's the definition of multiple. We say an integer n, I should have written that m and n are integers here. We say that an integer m is a multiple of an integer n if there exists a k and z such that m is n times k. And so note, anytime you're talking about multiples, there's two numbers automatically involved, and this relationship is not symmetric. Something is a multiple of the other, but not the other way around most of the time because of the way integers work. Now, if you want to express it the other way, then we will say that n is a divisor of m, or that n divides m. Okay. And the notation for this is that. This little vertical bar here says n divides m, or m is a multiple of n. Okay. So this whole circle of different words is all a bunch of different ways of saying the same thing based on which thing you want to emphasize. So often you'll, for example, want to talk about the divisors of a particular number. So you might talk about the divisors of 24, in which case you're talking about numbers like 3, 8, and 12. Or you might want to talk about the multiples of 24, in which case you're talking about 24, 48, 72, etc., numbers like that. Okay. And so you could express all of this in terms of only one of these words, but it makes language a little bit more flexible if we use all of these. Now, this all connects to the division algorithm, because the division algorithm says that if you look at all integers, they can all be divided into buckets. And so there's the nk bucket, the nk plus 1 bucket, the nk plus 2 bucket, and so on up to the, and then so this would be the nk plus n minus 1 bucket. And being a multiple of n exactly means that you're in this bucket. Okay. And that's not for any profound reason. It's just that literally being a multiple of n means that you have the form n times k, which is exactly what it means to be in this particular bucket from the division algorithm. Okay, so there are lots of questions about the division algorithm, so let's try and dig into some of these. So someone asks if the division algorithm is only for questions about multiples. And, I mean, the division algorithm is just a theorem that is true, so you can use it on any question about anything. Now, will it often connect to things about multiples? Yes. But it may be that a question is really about multiples and you don't realize it at first, so it definitely can show up there, or it might be also about these other buckets. So I think it's not quite true to say that the division algorithm is only useful if a question is about multiples, although any time when the division algorithm is useful, it means that there's multiples lurking around somewhere in the background. Someone asks about proving a there exists statement, and they say, if you're proving a there exists statement, does it suffice to give an example? And the answer is yes, but be careful. Okay. So this statement can be proven by example. But here's the thing you have to look out for. You might have something where you have a statement that looks like for every y in t, there exists x in S such that blah, blah, blah. Okay. This is not a this is not a there exists statement. So I think the time when people get most confused is when you have a for every and a there exists statement stacked in this order, where there's a for every statement out front and a there exists statement inside. And so whenever you're proving a statement like this, what you're basically going to end up having to do is not give one example, but give infinitely many examples. Namely, you're going to have to give a particular example of x for every y. Someone asks, and this is an excellent question, when writing out a proof with a bunch of algebra in it, how much algebra do you have to show? And I will say you can certainly skip some algebra. And so this is the joy of the fact that you're probably going to do your proof on paper first and then write it up. You don't have to write every step. Now, don't skip so much algebra that you're not really saying anything, but this is definitely an instance where you can, quote unquote, add by subtracting, by which I mean that you can make your explanation of a proof clearer if you show less, because what you're doing then is you're hopefully hiding the trivial steps, that is the like squaring of x plus y or something like that, and emphasizing the non-trivial steps. So, yes, you can skip some steps in algebra, but make sure if you do that they're very, very easy steps that anyone who was taking a 200 level math class could fill in. But don't skip any steps in the proof part, but you can skip steps in the algebra part, I should emphasize. Getting into proof by contrapositive, someone asks, should you look at the contrapositive right away, or should you start with direct proof? And for me, the answer here depends on the statement. So your default setting should be that you start with looking for direct proof. Okay. But you don't always have to rely on the default. There are, as we've talked about, these telltale signs that something might really be a contrapositive question. And so I've listed these in the videos, but I want to sort of just re-emphasize what are some signs something might be a contrapositive question. And then that might mean you start by writing down the contrapositive rather than that might mean you start by writing down the contrapositive and trying to prove that rather than starting with direct proof. Okay. So one big one is an or in the conclusion. By the conclusion here, I mean that you're being asked to prove an implication if blah, then blah. If there's an or in the then piece, that's often a sign that the contrapositive is going to look nicer. Okay. Another time is when the conclusion is about x, y, n, etc. When the conclusion is about a specific variable, but the hypothesis is about some complicated formula involving these. So, in other words, if your hypothesis is about something like xy squared minus 7, and your conclusion is that x is odd, I can all but guarantee you that you're looking at a contrapositive question. And the last telltale sign that something involves a contrapositive that we've talked about is lots of appearances of the word not. Okay. And so if your hypothesis or conclusion is about something not being equal to 5, then the contrapositive will, of course, negate that, which will turn the hypothesis that something is not 5 into the hypothesis that something is 5, and that will make your life much easier. Okay, so if the hypothesis is about something not being a multiple of 3, or what have you, various forms of that sort of thing, then you want to look at maybe the contrapositive is nicer. Okay. So I should correct myself, by the way. I said something like if the hypothesis is that x is not 5, then it turns it into something where the hypothesis is x is 5. That's not right. If the hypothesis is something about x not being 5, then it turns it into something where the conclusion is something about x being equal to 5. Because remember that the contrapositive negates both pieces and flips them. Someone asks, going back to the division algorithm and the fact that I've stressed in the division algorithm that this Q and R you find are unique. Someone asks, isn't the fact that for a particular B there are lots of R's that are possible, doesn't that contradict the uniqueness? And so remember, if, say, B is 5 in the division algorithm, then remember that R can be anything that is at least 0, but strictly less than 5. And so the question is, isn't the fact that if B is 5, R can be any of these 5 different things, doesn't that contradict the uniqueness part? Okay. And the division algorithm gives you a unique Q and R only for a particular pair of A and B. So it's not just for B, it's for both A and B together that there's a unique Q and R. Someone asks about what would a division algorithm question on a test or quiz look like, and not to be cheeky, but the answer is it would look like the division algorithm questions on the homework. So it would be, for example, a proof that asks you about something being a multiple of 4 or a multiple of 3 or a multiple of 8. Anything that involves that kind of thing is very likely to require the division algorithm. So it is now just a tool that you can apply wherever it fits. Okay. There are some questions about specific questions on the homework, which I will go over in a second. But before I go into specific questions from the homework, are there general questions about direct proof, the division algorithm, proof by contrapositive, that people want to talk about? Okay, so the questions that I have requests to talk about seem to be 14, 16, 22, that's all I'm seeing, but are there any other questions? You can just throw a number in the chat if you like, that people would like me to touch on from the homework. $19. Okay, so let's talk about these. All right, and I won't do all of them, but I'll at least give you some guidance on what this looks like. So for 14, and I'm going to encourage you to look at the PDF so I don't have to copy the question, but 14 is about a, b, c, x, and y being integers. And it asks you to prove that if a and b are multiples of c, then so is ax plus by. Okay. So just to remind you sort of the format, I'm going to suppose the if part. So I'm going to suppose a and b are multiples of c. Okay. And then what does that mean? That means there exist k and l in Z. Such that A is k times C and B is L times C. And all I've done here is spell out the definition of multiple. Okay. Again, make super sure when you're doing this kind of thing that you use a different K for A and B. So I definitely can't say A is K times C and B is K times C, because if I do that, what I'm secretly assuming is that A and B are equal, which I don't have any reason to assume in particular. So then after you have written out that, then I can look at this AX plus BY. And so that is KCX plus LCY. And that is C times KX plus LY. And so now if I go ahead and let's say M be this thing, well, then AX plus BY is M times C, and that exactly means that AX plus BY is a multiple of C, by definition of multiple. I'm going to proceed, but if there are questions, throw them in the chat and I will back up as is appropriate. Okay, 16 is, I think, very mysterious looking. Which is namely, it says, prove that if M is even, but not doubly even, then M plus 2 is doubly even. Okay, so you have no real choice but to start by supposing that M is in Z and is doubly even, or sorry, is even, but not doubly even. Okay. So the fact that it's even means that there exists a K such that M is 2K. Okay, and now here's where we have to think slightly creatively about how are we going to use the not doubly even hypothesis. Okay, I could spell out not doubly even means that there don't exist even integers x and y such that M is x times y. Or even for every pair of even integers x and y, M is not equal to x times y. But if I actually look at this thing right here, I can apply the fact that M is not doubly even to deduce something about K. Namely, because M is not doubly even, this K has to be odd. Because if this K was even, what would that tell me? Well, then M would be a product of 2, which is even, with an even number, which would mean M was doubly even. But M isn't doubly even. Okay. So okay, so this is really the key step of this whole question. And once you have this step, it all falls into place. But are there questions about this step in particular? Well, what happens from here? So it's m plus 2 we care about, is 2 times 2l plus 1 plus 2, which is 4l plus 4, which is 2 times 2l plus 2. Okay. But this is even, and this is even, so that shows you that m plus 2 is doubly even. By the way, I should note there's two halves to all of these questions, right? There's the half about figuring out why the thing is true. And so I basically just argued for you sort of how that works. But then I didn't actually write up a complete proof of it. There's also the, okay, I understand the solution. How do I write it? And so I try and interpret the spirit of questions and answer either, is the person asking about what is the solution versus the person is asking, how do I write the solution, which are both well within the curriculum of the course. But usually someone who's figuring out what the solution is doesn't want to hear about the details of writing it up and vice versa. So in lecture, when I write stuff down, I'm going to sort of alternate between writing it formally and then just sort of showing you scratch work that you could use to turn the scratch work into a proof, as we talk about a lot. But if your question is ever about specifically how do I write up the solution to exercise whatever, let me know and I will happily talk to you about that. Okay. In the videos outside of class, I try and always write everything up as though it was a final solution. So it should all be things that if you turned in, I would give you credit for. Whereas in class, I'll sort of juggle back and forth again on what's being asked. But appropriately use that. Thomas, yeah, sure, that's fine. So you're doing something very similar. So since k is odd, k plus 1 is even. And so then you've written this as 2 times k plus 1. That is also perfectly acceptable. I think I effectively just wrote down a proof that if k is odd, k plus 1 is even, when I was sort of sketching out this list, or this proof that I gave you. Okay, so 19. And this actually goes right back to the question we talked about earlier. So this asks you to prove or disprove that if A and B are sets, then there exists a set C such that A union C equals B union C. Okay. So earlier it was asked, can you prove a there exists statement just by giving an example? And so this question may have even been asked specifically with this homework question in mind. Okay. And if you look at this and you don't think about it too carefully, it's very easy to see, okay, there's a there exists. And so then it looks like this is something I can prove with an example. Okay. But please note, this is a for every statement. Okay. Why is it a for every statement? Because this part at the beginning where it says if A and B are sets, then blah, 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 blah. This if A and B are sets, this is really just saying for all sets A and B, there exists a set C such that A union C equals B union C. Okay. In other words, this is exactly that kind of question we talked about before, where this is the for every there exists flavor of question. And so what I really have to do here in order to prove that this is true, and I will spoil this is true, we need to prove this by giving an example of C for each possible pair of A and B. And so, of course, there's infinitely many pairs of A and B, so I'm not going to give you a list where I list every A and every B. What I'm really going to do is give you a formula to tell you, for a particular A and B, how do you choose a C that makes this true? Okay. And so, here is my hint. Choose C to be A union B. If C is A union B, then I think it's not so difficult to convince yourself that A union C is in fact C, and B union C is in fact C, and so A union C equals B union C. Okay. But note what I'm doing here is not giving one example where I say, like, well, if A was 1, 2, 3 and B was 4, 5, 6, then I could pick C to be 1, 2, 3, 4, 5, 6. I don't get away with giving just one example like that. I have to actually give one example for every possible pair of A and B I could choose. And so sorting this out, when is something secretly a for every statement, is one of the sort of nuances of the language that's being used here that we have to sort of sort out as we go through this. So I got a lot of questions about 22, and I think that's because 22 actually asks you to prove, I think that's because 22 actually asks you to do one more step than most of these. Because number 22 doesn't actually tell you what it is you're trying to prove. It asks you to figure out what you're trying to prove and then prove it. Okay. And so what this is really asking for you to say is an answer that looks like, for n in Z, n squared minus 5 is a multiple of 4 if and only if and then you have to fill in the blank, and then you have to prove the statement, which is you have to prove the if and only if. Now, I believe you will come up to, with your if and only if, I think you're going to come up with n is odd as your thing that goes in the blank. But then you have to prove that if n is odd, then, so I think it works out like this. But you have to figure this out, and there's a bunch of different ways you could figure out that this is what goes through here by like doing a bunch of examples and guessing, or you could find a more systematic way to do it. Okay. But then your proof here, and I want to just mention what happens when you're going to prove an if and only if statement. I have to prove it in two directions. So I have to prove if n squared minus 5 is a multiple of 5, then n is odd. And I also have to prove if n is odd, then n squared minus 5 is a multiple of 4. Okay. Okay. Why aren't we just proving if n is odd, then n squared minus 5 is a multiple of 4? Okay. That is a good question. And the answer is because then I'm not really answering the question of which integers make this thing a multiple of 4. What you've really done, if you just prove that if n is odd, then n squared minus 5 is a multiple of 4, what you've really done then is just to say, well, these are some of the integers where n squared minus 5 is a multiple of 4, all the odd ones, but you have not excluded the possibility that there are others. And so, in other words, if you call the set of such integers S, if you prove what you've suggested in the chat, May, what you've proven is the set of even integers, sorry, the set of odd integers, is a subset of S, but you haven't proven that it's equal to S. Does that make sense? Okay, so writing this out, this is a pretty straightforward direct proof. This, though, is a perfect example of something that we should prove by proving the contrapositive. Okay. Which you might rightly point out, wait, isn't this homework before the proof by contrapositives? Which is because I reordered the sections to try and make the calendar work better. But apologies, this is something we really want to prove by contrapositive. Okay. And how do I know we want to prove this by contrapositive? Just by looking at it? Well, if you go back to our list of things that you want to prove by contrapositive, this is a perfect example of this one, where we have a hypothesis about a formula and a conclusion about a variable. Here the hypothesis is about n squared minus 5, and the conclusion is about n. I'd much rather it be the other way around. I'd much rather have a hypothesis about n and then prove something about n squared minus 5. Sorry, this is supposed to be a 4, by the way. Okay. And so here we get to suppose n is even. So n is 2k for some k and z. So n squared minus 5 is 2k squared minus 5. It's going to be 4k squared minus 5. Okay. And I'm going to rewrite this in a slightly strange way, and you'll see why in a second. Okay. So I'm doing this so that what I'm showing here is that actually, in the case that k is even, the number I've gotten is in the 4k plus 3 bucket. Remember, the division algorithm breaks everything into buckets, where there's the multiple of 4 bucket, the multiple of 4 plus 1 bucket, the multiple of 4 plus 2 bucket, and the multiple of 4 plus 3 bucket. I had to jostle this minus 5 a bit to get it to turn into one of those 4 buckets. And namely, it's in the multiple of 4 plus 3 bucket. And the fact that it's in the multiple of 4 plus 3 bucket tells me that, in fact, it is not a multiple of 4. Okay. So someone in the questions asked more specifically, isn't it possible I did this question without using the division algorithm? And I think there are solutions to this I would accept where you did not mention the words division algorithm. But when you end up saying this thing's not a multiple of 4, you are using the division algorithm because you're saying, okay, this thing can be written so that it's in the 4 times a multiple of something plus 3 bucket. So it can't be in the 4 times something multiple of 4 bucket. Okay. So those are my questions. Or sorry, so those are your questions that you've said. Are there any other questions people want to ask before I let you go to look at the quiz? Okay, well, hearing no questions, I will go ahead and make the quiz visible, so you should be able to see it now. It should have the PDF there. The quiz only requires direct proof, just so that you know. The test will, of course, cover the other 2 things, but the quiz is really just to give you a little bit of direct feedback from me about how you're writing up your proofs. Have a wonderful afternoon. Please email me or come to office hours if you have any questions. I'll post the test so it shows up on Friday, so we won't meet on YouTube. But email me if anything comes up as an issue during the test, of course. Like the test doesn't post or whatever, who knows. And I will see you all on Monday. And I will send you an email before Monday that will basically remind you that by Monday you should have watched the videos on proof by cases, which I think are already up, but which will be up by then. All right, have a wonderful afternoon. And I will see you on Monday.